In the physics curriculum, usually first one teaches classical mechanics, and then based on that, one teaches quantum mechanics. However, we won't be doing it that way. So we'll be teaching you quantum mechanics for mathematicians from scratch, without, at least in the beginning, without making reference to classical mechanics. There will be a little bit of classical mechanics which will show up from time to time, and then I will tell you that. So you don't need any preliminary knowledge of quantum or classical mechanics, but just to tell you that how we're going to teach you, it's somewhat different from the standard method. And then maybe later on in your academic life you will encounter it, you will see it. So then, okay, what about the elephant? You know, the elephant refers to the tale of blind wise men who decide to study an elephant. And then, you know, the tail, right? Some of them touch the trunk, and some of them touch the leg, and some of them touch the stomach, whatever. They touch different parts of an elephant, and they give a very, very different description of this thing, even though that's one animal. That's a little bit the same story about quantum mechanics and mathematicians. So that's roughly, you know, quantum mechanics in physics is one topic. But quantum mechanics in mathematics is many, many topics. Roughly speaking, like mathematicians are blind and they're touching that elephant, and different people from different mathematical topics, they touch it and they see very, very different things. So in fact, to be honest, the subject of the course, quantum mechanics for mathematicians, roughly speaking, does not exist. So what we're going to do, let's say, at least this is the ambition for the plan of the course. So we'll start with interaction of quantum mechanics with algebra. And then we'll talk of how it looks in functional analysis. And then we'll try to discuss some differential equations. So then possibly some probability. And if it converges, we'll end up with geometry. Of course, that's a very, very ambitious plan, so it's not entirely clear that it will all work out, but at least that's the idea. So how quantum mechanics is represented in different fields of mathematics. Of course, also a standard disclaimer, of course, in such a course, some things I will prove, some things I will prove by example. Some of the things maybe I don't prove at all in some way. So, and of course, it's all a little bit of surfing, right? It's not an in-depth math course where you take one topic and you dig in and you understand everything about the subject afterwards. So, but on the other hand, we'll see many different things, and hopefully we'll see. Hopefully it will be interesting for all of us. So, do you have any questions or worries about the course plan? If not, maybe we can just start with basics of quantum mechanics. And today the topic is axioms of QM. So, of course, here again the word axioms probably one should take with a grain of salt. It's not going to be exactly the axioms in our mathematical sense of the word, but some kind of axioms. So let's start with the first one. Here, from time to time, or actually often, we'll be using the word a quantum system. Well, so this word has no definition, but well, quantum system, that's the system that we want to describe in quantum mechanics, and basically the axioms will tell us what the meaning of a quantum system, what of the words quantum system is. All right, so to a quantum system in quantum mechanics, one associates H a Hilbert space over complex numbers. So for the words Hilbert space, I will now give a definition, but let's say since we're now targeting the algebra part of the story, for the first maybe 3 or 4 classes, I will be assuming that this space is a finite dimensional vector space. It carries a Hermitian product. So let me recall from the standard linear algebra course. Actually, most of what we're going to discuss today is standard linear algebra. Well, what are the defining properties of Hermitian products? Well, it is usually linear in one of the vectors and anti-linear in the other one. Here, an interesting story starts. Physicists and mathematicians, they choose those vectors differently. So mathematicians think that it should be linear in the first vector, and physicists think it should be linear in the second one. So, okay, in this case, let's follow the physicist notation. But you should know that mathematicians typically do it differently. So, so here we're using the physics notation. So this is linear in the second vector. So the second property says that if you exchange the order, you get a complex conjugation. And the third property says that for the same vector, the product is always real, and there is a non-degeneracy that it is 0 if and only if u is 0. So then the square root of this product is a norm on H. Right. So in fact, one would think about physics and mathematics. So physicists are also using a somewhat different notation. So maybe I should show you this notation, and maybe we'll be even using it from time to time, but not very often. So physicists prefer, instead of those roundish brackets, so they prefer to write it in this way. And so since these are those angle brackets, they also say that these are bra vectors and these are cat vectors. So that's the funny language which is sometimes used in the physics literature, but okay, the meaning is still the same, right? Roundish or angle brackets, that's still a Hermitian product. Maybe just to recall again from the standard linear algebra book. So what are the important things to remember? About Hilbert spaces, or about spaces with Hermitian products. First of all, perhaps the dual space is canonically isomorphic to H, and this isomorphism is organized as follows. So you take a vector here, let's say V, and it is mapped to a linear functional, LV, which sends vectors to those Hermitian products, right? So in particular, every linear functional is of that form. It's a Hermitian product with some vector in the Hilbert space. So that's probably one interesting property. Another interesting property, if you have an operator, an endomorphism of H, then in the Hilbert space you canonically associate to it another operator, the conjugate operator. So another operator, A star, such that so this property holds true for any pair of vectors in H. Right. In particular, an operator with these properties always exists and it's unique. Right. So the next property is geometric. Suppose that we have a subspace, a vector subspace of the Hilbert space. So then there is canonically another subspace which is denoted V orthogonal. This is a subspace of vectors which have a vanishing Hermitian pairing with vectors of V. And so this is a direct sum decomposition, meaning that for any vector, there are unique, let me call them V parallel in V and V orthogonal in V orthogonal. Such that our vector admits a decomposition. So up to now, no worries, right? Everybody knows it very well. I'm just recalling you some first year linear algebra stuff. Now, assuming that we are in this situation, assuming that we have a subspace, so we defined its orthogonal with respect to the Hermitian pairing, we can define PV, an endomorphism, of H, such that, for instance, in terms of this decomposition, PV of V will be equal to V parallel. So it's equal to identity on V, and it vanishes on V orthogonal. Right? So this is the orthogonal projection on the subspace V. It's easy to check that it has the following properties. Of course, as every projection, it squares to itself, right? So the square of a projection is always the same projection. And in addition, it has a property that this Hermitian conjugate of PV is equal to itself. And in fact, these properties characterize orthogonal projections. So if you have an operator which has these two properties, then the image of PV is a subspace, and PV is the orthogonal projection on that subspace. Up to now, how is it going? So very easy, right? Okay. Good. Maybe one more thing that I want to say about it. And you probably need it later on. So suppose that the dimension of V is equal to 1. And let's choose a vector of V of norm 1, so of length 1. So then I can write an explicit formula for the for the projection operator. So PV acting on a vector V, this will be equal to the Hermitian product of E with V multiplied with E. Sometimes one uses various notations to express it, and I think one possible mathematical notation will be like this, and one possible physics notation will be like this. But they all say the same thing, right? So that's the formula that they have in mind. Now, if the dimension of V is greater than 1, then there is an analogous formula which is somewhat more complicated. So in this case, we need to choose an orthonormal basis of V such that those Hermitian products are equal to 0 if I and j are different, and equal to 1 if they are the same. And in this case, the projection has this formula. All right, so that's a short crash course on the elementary properties of complex vector spaces with Hermitian products, or finite dimensional Hilbert spaces. So, and recall that this was a kind of excursion which was triggered by the axiom 1. And the axiom 1 was saying that when you have a quantum system, you associate to it such a vector space. So now let's go to the axiom 2. And this goes under the name of observables. So observables, these are the things that will be eventually, or physicists will be eventually able to measure in the quantum system. And so observables first of all, so these are linear operators on H. which have a property that A star is equal to A. So they are self-adjoint operators. And in fact, especially in the functional analysis part, when we allow H to be infinite dimensional, we will have to spend some time discussing this notion and how it works. However, if it is all finite dimensional, so then in some way it's all easy. And I recall another chapter from the first year linear algebra, and that's the Spectral Theorem. All right, now what does it say, the Spectral Theorem? So you have a self-adjoint operator on a vector space with a Hermitian product. Now there is this Spectral Theorem, and so what is it saying, this Spectral Theorem?
The eigenvalues are real.
Sure, there are things which are called eigenvalues. They are real. But what is it for you? What's the statement of the Spectral Theorem? All right, okay, let me try to say it, and then you tell me your comments whether this is the Spectral Theorem for you. So, okay, there will be several versions, but let me start with the following. So there are real numbers. Let's say lambda 1, lambda k. So in mathematics, we call it the spectrum of A. And so there are subspaces of H, V1, Vk. So they are orthogonal to each other if I is different from J. And H is a direct sum of those subspaces. This means that every vector of H is uniquely representable as a sum of vectors in those K subspaces. So every vector admits a decomposition of this form. And the operator A admits a decomposition which is like this. Where Pi is the orthogonal projector on Vi. Right? So that's the great formula. So every self-adjoint operator is encoded in those data. There is some number of eigenvalues. You see here, let's say, let's assume that the dimension of H is equal to n, and the dimensions of Vi are equal to Ni. So then this direct sum decomposition tells us that the sum of the dimensions of the subspaces is equal to the dimension of the total space. And so on each of those subspaces, A acts as a multiplication by some real number, lambda I, and so that's So that's the formula. Of course, yeah, I don't know whether for all of you this is how you think of the spectral theorem. Maybe some of you think of diagonalization of a Hermitian matrix, which has then real eigenvalues, those lambdas, on the diagonal. Now, maybe a small remark. Sometimes it will be more convenient for me to write those spectral decompositions with a sum not from 1 to k. So this is the sum over distinct eigenvalues. But sometimes it is more convenient to write it as a sum from 1 to n. And let me call it j from 1 to n, lambda j, pj, where pj will be projectors on one-dimensional subspaces, and lambda j may repeat. Right? So that's also a possibility. So that's actually what happens here. You see, you have a projector on a vector space of dimension k, and this is actually, if you compare the two formulas, this is a sum of k projectors on the spaces spanned by EIs, right? So in principle, sometimes it is convenient to stress in the spectral theorem formula that there are terms corresponding to each distinct eigenvalue. And this decomposition is unique. So this presentation is unique. Now, or it might be more convenient to stress that if you have an n-dimensional space, you have n terms, which are all of a very simple form. So those decompositions are in general not unique, right? Because you can choose different orthonormal bases in each eigenspace, right? Okay, very well. Now, perhaps just a small example. So in the physics language, it's called a spin 1/2 particle, or this is one possibility to call it a spin 1/2 particle. And this is an example where I choose h equal to c2. That's, of course, the first more or less interesting choice. Well, in this case, the dimension of the space of observables is equal to 4. So this is actually a real dimension. So note that the space of observables is naturally a real vector space. Right? If you multiply by a complex number, then the property of being self-adjoint may be broken, but if you multiply by a real number, it stays intact. So, and there is a nice basis in A. So let me write it as matrices. Right? So this is C2. Operators on C2 are 2 by 2 matrices. So I'm choosing the standard Hermitian product. Should I write it? What is the standard Hermitian product on C2? Right? and 3 matrices which are known as Pauli matrices. So sometimes they're labeled with numbers, sometimes they're labeled with coordinate axes. So how is it? Is it obvious that they're all self-adjoint? And probably you can imagine that they span this A. Okay. So these are Pauli matrices. So any operator A is a linear combination of those. Maybe just an example. Of course, that's a very simple example of using this spectral theorem. For instance, this guy sigma 3. Well, what are the eigenvalues of this guy? 1 and minus 1, right? So this is 1 times so these two guys are spectral orthogonal projections, and these guys are eigenvalues. Right? So that's an example of a formula. Of course, a very, very simple example. Okay, very well. So that's the notion of observables. Now let's go to the next axiom. And this is called states. So you imagine a system, right? You can measure something, but then this system can also be in a different position or in a different state. At least that's what we can imagine. So again, there is some set, which is a set of states. Let me call the elements of this set M. So these are again operators on H. They again self-adjoint. They have a trace equal to 1. And they're positive. Who knows what does it mean positive? Mm-hmm.
It's like if you take x and x, then it will be difficult.
That's right. So that's one possible way to say it. So u mu is non-negative for all u and h. In fact, there is another way to say it, an equivalent way to say it. So, well, recall, since this is a self-adjoint operator, we have a spectral decomposition of it, right? So this is a sum from 1 to k MIPI. Now, in fact, this positivity is a statement about the eigenvalues. So we say that all MIs are greater or equal to 0, right? So these are two equivalent statements, two equivalent characterizations of this property, m greater or equal to 0. Now, by the way, since we wrote it in terms of this spectral decomposition, so what does this mean, right? Trace equal to 1. Recall that trace is equal to the sum of all eigenvalues, right? So trace m is equal to 1. This is the same as sum of mi's times the multiplicities, which is equal to 1. So from here comes the following notion. Which is called pure states. So a pure state is a state where in this sum you have only one term, and since you have only one term, you have to have m is equal to 1, right? So in other words, it looks as follows. M is equal to, well, 1 times the projector, and let me call this projector PE. Remember, we had a projector, so this is a projector on a one-dimensional space, right?
I guess you mean as well that m should be rank 1. Else, I mean, it could be just one sum and just identity with 1 over n over 1 over.
Yeah, sure. Yeah, sorry. Yeah, you're right. So let me choose this extremal case. K is equal to 1, the dimension of the space is equal to 1, then, you're right, then m equal to 1, and m is equal to PE for some E in H, and I recall that PEV is given by this formula. So these states are called pure states. All the other states in physics are usually called mixed states. And again, this spectral theorem or spectral formula shows you that the mixed states are convex linear combinations of pure states. Right? Every mixed state is a sum of one-dimensional projections with coefficients, positive coefficients, with sum equal to 1. So this is called a convex linear combination. Convex linear combinations of pure states. Maybe now one mathematically trivial but physically important remark. You know, sometimes it happens, right? Kind of between math and physics, things may be trivial on one side and important on the other side, and the other way around. So a remark. So let's return to pure states, right? So suppose we have a pure state. A pure state is essentially a projection on a one-dimensional subspace. So suppose that M is equal to PE. Now, let's take a complex number of absolute value 1. And let's consider a projector defined by the vector ZE. So what's the relation between this guy and this guy?
Equal.
Of course, they are the same, right? Because, okay, we consider a very, very simple situation. We have a one-dimensional subspace, and we consider orthogonal bases in that subspace. A basis in a one-dimensional subspace consists of one vector. And there is not much of a choice. That's basically all the choice you have. So these are all the vectors of length 1. So, of course, right? So this is, nevertheless, let me write this trivial formula, right? Recall that in the first, according to our physics notation, it's antilinear in the first factor. So we have z bar times z times EVE, and this is equal to absolute value of z squared PE, and this is equal to PE. So in other words, if you change the phase, the observable M remains the same. Maybe let me express it in the following way. So S pure is isomorphic to the projective space of the Hilbert space H. In other words, to the space of lines in the Hilbert space. Or, since these are all finite dimensional vector spaces, right? H is always isomorphic to some Cn for some n. Right? And then this is simply isomorphic to Cpn. Okay, that was a trivial mathematical observation. I said that it was physically important. So why is it physically important? That's because we often, let's say, in many cases, or maybe in most part of the course, we'll be interested in pure states. We're less interested in mixed states because it's a more exotic theory. So usually people focus on pure states. So now about pure states, we now have two ways to think. So this is a one-dimensional projector, or this is a vector. Vector up to multiplication by a complex number of absolute value equal to 1. So in physics, more often we think of pure states. Well, okay, let me write something. So pure states, so that's the same thing as vectors in H of length 1 modulo the equivalence E multiplied by Z, where Z is a complex number of absolute value equal to 1. So nevertheless, we often think of E as a pure state, and we forget about the equivalence. So this is very, very often. Of course, it's not entirely true, but then, like we'll see, hopefully, if in the end we do come to the geometry chapter, then we can try to revive this definition and understand how to get rid of this quotient. So this presentation of pure states, those E's, they are sometimes called wave vectors or wave functions. And that's a very, very important presentation of pure states in physics. In mathematics, people more often think about it as projections or subspaces, but in physics, they usually think of them as of actual vectors. And this will be important starting from maybe next hour or maybe next lecture. So we'll often use this picture, even though it is somewhat wrong. All right, so we have one more axiom. I suggest to make a break. So we come back at 10:15 and we do the last axiom and we start discussing other things in quantum mechanics. All right, so let's continue. So now the fourth and for a moment the last axiom. Even though we'll see, maybe we'll be able to come to the fifth even today, but which goes under the name of measurements. So you probably heard, or some of you know very well, some of you heard, that the quantum mechanics is a probabilistic topic. So it's related to probability. And so here the idea is as follows. So to an observable, so the things that we're supposed to measure, and to a state, we associate, let's say, so to a pair of an observable and a state, we associate a probability measure on the real line. Let's call it mu am. And that's the probability measure for the outcome of the measurement of the observable A in the state defined by M. So that's of course the physics, whatever words, whatever it is, for the outcome of observation of A in the state M. Now, so this measure is defined by a concrete formula. And perhaps for the finite dimensional case, I will make it somewhat more complicated than needed. And then in the infinite dimensional case, it will probably serve to make our life a bit easier. So, so we'll do it in two steps. So step one, we take an observable A and we associate to A what is called a projection valued measure on the real line. So any of you ever heard about those projection valued measures? All right, so let me tell you what they are. So suppose you have a measurable subset of the real line. Then to this subset, you associate P of E. An orthogonal projection in some Hilbert space H. So to each subset, we would associate a projection. Now those projections will have the following properties. So the projection of the empty set will be 0. The projection associated to the whole real line will be the identity operator on H. And similar to the ordinary properties of measures, suppose you have a sequence of subsets which do not intersect if I is not equal to j. So then P of the disjoint union is equal to the sum of this infinite series, and in particular it says that this infinite series converges. So the series converges, it converges to this value. So I'll show you in a moment examples which correspond to the finite dimensional situation. In fact, as I say, this language is a little bit prepared for the future, for the infinite dimensional case. In the finite dimensional case, this all is, we'll see, is very simple. But maybe now just a small remark. So this holds for infinite families, but of course it also holds for finite families. So if you have E1 which doesn't intersect E2, we have P of E equal P of E1 plus P of E2, where E is the union of E1 and E2. In fact, maybe, right, that's linear algebra, maybe take it as an exercise. So that's the situation. We have two orthogonal projections, and their sum is also an orthogonal projection. So what does it mean geometrically? How this can be? What do you think? What are the options? How this may happen? So I want to know how it looks geometrically. Oh, no. Yeah. Right. What are the?
So they are orthogonal.
Right. I guess the only geometric situation where it is feasible is if the images are orthogonal. So then, of course, P of E is a projection on the direct sum. So if you have two orthogonal subspaces, you take their direct sum, that's a new subspace, and P of E is a projection on this direct sum. Right? So let's call this V1, let's call this V2, and P of E is a projection on V1 plus V2. So this is actually true, and maybe it's a good idea if you try to prove it. So another thing which also follows, and kind of once this is correct, it's easy to show that if you take an intersection of E1 and 2, now forget this condition. Let's assume that the intersection is perhaps non-trivial. So then this will simply be a product of the two projections. In fact, it turns out that all the projections commute with each other. So it doesn't matter in which order you place it. So in fact, this one equation, it poses many conditions on this family of projections. All right, so now let me show you the projection valued measures associated to our finite dimensional self-adjoint operators. So we have a self-adjoint operator, and well, recall that this self-adjoint operator admits a spectral decomposition. So then I should associate to it this projection valued measure, and this means that for any measurable set of the real line, I should associate a projector. So what will it be? So this will be the sum over I, such that lambda I is contained in E of the spectral projections Pi. So that's our real line. So these are the eigenvalues. And now I take a subset, whatever it is, right? So that's my E. Now that's very simple, this definition. I'm just looking which lambdas are in E. That's it. And I sum up the corresponding spectral projections. So I'll let you check that it actually satisfies the axioms. So there is no secret. It's very, very easy. Maybe one more piece of notation. Sometimes it is convenient to introduce a family with one parameter lambda, and this corresponds to E being a semi-axis from minus infinity to lambda. So this is an open semi-axis from minus infinity to lambda. So, of course, by this formula, this is simply a sum over I, such that lambda I is strictly smaller than lambda of PI's. So maybe again, let me try to draw a picture for PA of lambda. Of course, PA of lambda is not a number, right? It's a projection. So it's a little bit funny for me to try to draw a graph of it, but I still try to do it. So you see, if lambda is smaller than any of the eigenvalues, so then here there are no projections at all. So I get 0, right? So this P of lambda is 0 here. And then here at lambda 1, it jumps and it becomes P1. And it continues like that till here, where it jumps to P1 plus P2, and so on. And here there is a last jump, and after it, it's simply equal to the identity. So that's a kind of pictorial presentation of how PA of lambda looks like. All right. Now step 2. So now I want to define an ordinary measure on the real line. So now computing it on some measurable sets should give a number and not a projection. And here the formula is as follows. You take a trace of M multiplied by the projection PA of E. So here there are several properties. Maybe again I outsource to you, checking those properties. So one property would follow from the properties of the projection valued measure. It seems obvious that for the empty set we get 0, right? Since we had 0. Now, for the real line, we'll get trace of M multiplied by the identity operator, because that's the projection which corresponds to the real line. Now you see why we wanted this trace of M to be equal to 1. Right? Because we want a trace of M to be the probability measure corresponding to the real line, but the real line is everything, right? So it has to be equal to 1. So the result of some measurement, the sum of the results of all the probabilities of all the measurements has to be equal to 1 if we want some probability theory. And maybe a useful exercise is to show that all those expressions are positive and bounded by 1. So what is the property of M that you need to use here? Positivity, right? M doesn't have that many properties. The trace of M is equal to 1 that we used here, and actually that we're also going to use in this inequality. But in this inequality you need to use positivity of M. Right. So maybe now that's the general recipe. Sometimes it's also called the Born formula. But now how does it play in our simple finite dimensional context, right? So we have this expression for the spectral projection. So what's the formula for mu a m of E? Well, let's just make a substitution. So this is a trace of M and this is a trace of M times this sum over I, such that lambda I is an E of Pi. Well, let's just exchange the sum and the trace. And we obtain this. So that's the expression for our measure. Maybe two more formulas, right? With measures on R, I think we're all supposed to have a very good intuition about measures of R. So what kind of measure is it, right? It's now defined by an explicit formula. So let me introduce this measure of minus infinity lambda, right? So E is equal to minus infinity lambda. So similar to the projection valued story, this is equal to the sum over I, lambda I smaller than lambda, and here trace M pi. So how does this measure on the real line look like? What's the mathematical word for such a measure? So, for instance, does it look similar to the, say, what's the standard measure on the real line that we know? That's the Lebesgue measure. So is it like the Lebesgue measure? Not really. So such measures are called atomic measures, right? So this is an atomic measure. So there is a number of points, a finite number of points or atoms, and each atom has a weight. So those weights are these numbers, right? So maybe, so since you mentioned delta functions, sometimes it is convenient to write the density. So let me call the density. So when we write the density, we pretend that the measure is absolutely continuous with respect to the Lebesgue measure. Our measure is not, but still, like, the formula looks as follows. So this is a sum over I from 1 to k, and here there are those weights, trace of M pi, and here delta lambda minus lambda I. Maybe that's right, that's what you had in mind. So that's a density of the measure mu am. Right, so there are those atoms. So these are the possible outcomes, and that's now how in quantum mechanics you interpret the eigenvalues. So the eigenvalues of A, these are possible results of the experiments, and the numbers, the weights that we assign to them, so these are the probabilities of those outcomes. Maybe let's play with it for some more minutes. As I said, we often think of pure states. So for pure states, suppose that M is equal to mu, u is an h, and of course the length of u is equal to 1. Right? So then let's denote those weights by pi's. So the weight or probability of lambda I is given by this formula, trace of mu times pi. And now what is this? So this is a projector on the one-dimensional subspace spanned by U, and this is a spectral projector on the eigenspace corresponding to lambda I. Now let's consider the simpler case when the dimension of Vi is equal to 1. So then there is one basis vector, let's call it Ei in Vi. Of course, we can always choose it up to a phase. And in this case, maybe also some small exercise to show that this is given by the following nice formula. So we have two vectors, we have the corresponding two projections, and the trace of the product of these two projections is exactly equal to the square of the absolute value of the Hermitian product of the vectors. So that's one of the formulas that you often see in the physics literature. So here maybe one more word about the language. So of course this is also equal to, maybe I also write it in this form. So as we say, Pi is a probability to find our system with a value lambda I of the observable A. Now, it plays an important role in this theory, and there is a special name for this guy, for this Hermitian product. It's a kind of funny name. So in physics, it's called a probability amplitude. It's a kind of strange name, because if anything is an amplitude, that's an absolute value, right? But they want the amplitude to be a complex number. Whatever, for historical reasons, that's the name. So the Hermitian product of the two vectors is called a probability amplitude, and the square of its absolute value is the probability. So we'll probably return to it from time to time, but so here there is a big question that we're not going to touch too much, but in what way quantum theory or quantum mechanics is different from a probability theory, right? So because you see what happens now, this axiom 4 produces for us lots of probability distributions, right? So then one may wonder whether those probability distributions, they all just come from some big master distribution, right? We're now producing probability distributions for each observable, right? That's what now happens. And there is a whole science where this is one of the focal points. It's called quantum information theory. And I think next term you will have the whole course on the quantum information theory, where among other questions, that's probably one of the questions that you will be talking about. But maybe already now you should see that that's where it comes from. So the outcome of quantum mechanics is a huge set of probability distributions. Of course, kind of it's interesting, maybe it just comes from one big probability distribution for all those variables. So this is called the problem of hidden variables. So if there is such a distribution, then maybe you just don't need all this nonsense, all this quantum theory. Why do you need all those Hilbert spaces and stuff? Just do probability. In fact, it turns out that this is not true, that even I think now there are experiments which show that this you cannot do. So that the results provided by the quantum mechanics, you cannot put them all together and have a big picture coming from some usual distribution of some usual probability measure. But okay, we're not going to touch too much of it, but maybe you should have in mind a little bit that that's how it looks like. Maybe now one example and then a little bit more about the notation. So the example for today is this spin 1/2 particle. So H is equal to C2. Now let's make a more realistic quantum observable. We even introduce, for the pleasure of the physics kind of, to make it more physically authentic, we introduce here the Planck's constant h bar divided by 2 times sigma 3. Recall that we know all the observables in this theory. So let's take an observable proportional to sigma 3. Now someone asked me during the break, why do we call it spin 1/2 particle? What does it mean? So the idea is as follows. So there is a quantum particle and it has some kind of internal rotation. Now the meaning of this observable A is a projection of the angular momentum on the z-axis. So we have here the z-axis. So this particle rotates internally. It may be, for instance, an electron. An electron is a spin 1/2 particle. So it rotates and we project the angular momentum to the z-axis. So that's the observation that we supposedly make. So that's A. Now recall that this is equal to h/2 times 1, 0, 0 minus 1. And so this is equal to h/2 times this spectral projection plus minus h/2 times that spectral projection. So what is the projection valued measure? So we have, maybe I write what should I write something, or maybe let me first say what will be my state. So my state will be a pure state which corresponds to the first basis vector. So what is the corresponding matrix M? So it should be orthogonal projection on this vector. What's the orthogonal projection on this vector? Say it.
1, 0.
Yeah, right. So that's the first one, 1, 0, 0, 1. Now I can write this formula for the density, right? So rho A mu of lambda. This is this distribution. Now there will be a priori 2 terms in this distribution, but those 2 terms, they include traces of products. So the trace of this product is simply equal to 1. So this is h/2 delta lambda minus 1/2. And the trace of this product is simply equal to 0, right? So, and that's it. So what happens? We have this h/2. And the atomic measure is completely concentrated there, right? So there is only one outcome of the measurement, and the probability of this outcome is equal to 1, right? It's a somewhat boring probability measure, so it's bad for mass, but for physics, I assume it's very good, right? You have a prediction of what your measurement going to give, and this prediction is this probability 100%. So in fact, that's the general situation. If U is an eigenvector of A, so that's an example of a phenomenon that we observe in here. If U is a then rho A mu is an atomic measure, or mu, maybe better say mu, is an atomic measure with one atom and the eigenvalue corresponding to U. Now,
Sorry.
sure.
Isn't there a problem with the formula? So it shouldn't be delta of lambda minus h bar over 2.
Oh, yeah, you're right. Everything. So no coefficient, right? And here h over 2. Good. But you know, towards the end of the class, it's supposed to decay in some way, right? And then you should be more careful. You should not get asleep and... Why nobody else makes comments? Good. Now let's take another example. Let's say U is, for instance, this guy. Well, maybe it's difficult to immediately compute the corresponding projection, right? So it spans another line, and there is a projection, orthogonal projection on that line. I computed the projection, and it is this guy, if I'm not mistaken. So now, of course, there will be a different formula for rho. Now, let me try to write it correctly. So I think it will be h over 2, and then the trace of this guy times that guy. And, right, so, no, again, what am I saying? So, okay, so there will be a trace of these two guys, which is 1/2 times delta of lambda minus h over 2. That's one contribution. And then the other contribution, which is again 1/2, because the trace of this guy with that guy is again 1/2 times delta lambda plus h over 2. So now, it's certainly mathematically somewhat still not very exciting, but more interesting. Now, actually, with equal probability, with probability of 50%, we're getting two outcomes. Of course, physically, it's entirely unsatisfactory. Basically, it's saying that we know absolutely nothing, right? Whatever. Anyways, there were only two possible values, and each of them has a probability of 50%. So it's like kind of tossing of a coin. So there is no information for us, but, well, that's the distribution that we obtain. Maybe now two more words about the notation. First of all, from the standard probabilities theory, you know that if you want to compute the mean value, yeah, I don't quite know what notation to use for it. Let me use this one for a moment, but I'm still, maybe until next class, I'll think how to denote it. Right? How do you compute a mean value in probability? Well, you take your distribution. Well, here the distribution. You multiply it by lambda, and you integrate. Of course, here this integration is a little bit kind of, here I write a formula like this, but what I mean in fact is simply sum over I from 1 to k times those lambda i's, and there were those weights, the probabilities pi, right? So here this integral is simply a finite sum corresponding to our atomic measure. So that's the mean value of A in the state M. Like for instance, here it was h over 2, and here it was what? 0, right? Minus h over 2 times 1/2 plus h over 2 times 1/2. So another thing that people in probability often do, they compute the variance. So the variance is again an integral of lambda minus a bar squared. So here again, this just transforms into a finite sum. And usually we say that the variance is a square of the standard deviation. So that's a definition, probability definition of sigma A. Now, what was this variance in these two examples? Well, what's the variance here? It's 0, right? Because the mean value is h over 2. The only value we have is h over 2. H over 2 minus h over 2 is 0, so there is only one term, and it is equal to 0. Now, what is the variance? What is the variance here? Here the mean value was 0, and lambda square is always h over 2 square. So the variance is h over 2 square, and sigma is simply this h over 2. So sigma is just huge. It's just because here we basically don't know anything about the spin or this moment of our particle. All right, maybe one more thing that I wanted to tell you before we stop. So there is something which is usually called, in the framework of the spectral theorem, a functional calculus. Suppose that you have a function of one variable, let's say f. So then for our observable A, we can define a function, f of A. Well, how is it done? One uses the spectral theorem. Maybe in general you don't know how to compute a function of an operator, but it's a function of one real variable, and so you know how to compute functions of eigenvalues. Right? So this is actually in some way a definition of this symbol f of A. So you're using functions of eigenvalues and you're using the spectral theorem. So now f of A is an operator. It's an operator, and if f is a real valued function, it's a self-adjoint operator. So given one observable, you get many more observables. Now, this is just a remark. Suppose you have such an observable, and you want to compute the mean value of this observable. So what would be the formula? Right? We're now, by the end of those 2 hours, we fully master quantum mechanics, right? We have an observable, we want to measure it, and we want to know what's the mean value. So how to write the answer in terms of those formulas, right? So now that's basically the same formula as there. But you simply replace a lambda with f of lambda. And this is equal to In fact, that's what we have done here, right? So this was actually an example of this formula where we just took a quadratic polynomial. Now we took more general function, and that's how it looks. So that's like a standard probability theory. Here we don't do, it's not specific for quantum mechanics. Right. All right, so that's it for today. I have perhaps one small remark about the exercise sessions. So today there will be the first exercise session where, of course, there is no homework. 15 minutes is probably not enough to to make a homework. But there, maybe in one of the problems, you should remove this Lie algebra question, because we will do Lie algebras. We'll do Lie algebras at the next class. And then for the in the second problem set, you will have some of the exercises which are marked as homework. And then I think we should agree that you hand them in before the next exercise class, which means next Monday at 11:15. All right, do you have questions? Adrien, you have questions? All right, so thanks, and that's it for today.